Today we'll talk about applications of equation of motion. During last lesson I derived most general form of equation of motion for uniformly accelerated and uniformly decelerated rectilinear motion. Then I said that equation for uniform motion we get if we put a, I mean acceleration, equal to 0 in this equation. In today's task we have two cars moving along straight line with constant speed. The first car departed from city A towards city C at 2 o'clock at 20 km per hour. The second car started from city B towards city C after 1 hour at 80 km per hour. The locations of the cities and their distances are shown in the drawing below. It is here, not below. Write the equations of motion for both cars, assuming that the coordinate of the city C is equal to 0. What time and where will the vehicles meet? The drawing is part of the data. Distance between cities A and B is equal to 400 kilometers. It's here. B and A. And distance between cities A and C is equal to 200 kilometers. A and C, 200 kilometers. To write equations of motion, we draw x-axis. It's here. Coordinate of city C is equal 0. So coordinate of city A is equal minus 200 kilometers and coordinate of city B is equal to minus 600 kilometers. Coordinate of city A is equal initial coordinate of position of first car x01. It's here. And coordinate of city B is equal to initial coordinate of position of second car x02. It's here. Here we have general form of equation of motion. T minus t0 is just time of motion. T is what clock shows in this moment, and t0 is initial time at the clock. If both cars began to move at the same time, and at the beginning the clock showed 0, we could replace t minus t0 by t. But not in this case, because cars began to move not at the same time. Cars move with constant speed, so acceleration is equal to 0. So the third expression in this equation is equal to 0. x0 is initial coordinate of position, and v is magnitude of velocity vector. In front of v we write plus if velocity vector is directed the same as axis, or minus if velocity vector is opposite to the axis. Vectors v1 here and v2 here are directed the same as x-axis, so in both equations of motion there will be plus in front of v here. Let's write the data. magnitude of velocity vector v1 is equal to 20 kilometers per hour here, and magnitude of velocity vector v2 is equal 80 kilometers per hour here. First car began to move at 2 o'clock here. Second, 1 hour later, so at 3 o'clock here. Coordinates of initial positions of cars equal to minus 200 and minus 600 kilometers. It's here. We see it here and here. Now we can write equation of motion for first car. Here is plus, because velocity vector v1 is directed the same as x-axis. You can see it here, v1 and x-axis. We put data to this equation and we have final equation here. That's final equation. We do the same for second car. Here is plus, because velocity vector v2 is directed the same as x-axis. You can see it here, v2 and x-axis. We put data to this equation, and here we have final equation of motion for second car. Here, final equation. These two equations allow us to calculate coordinate of position of both cars at an hour if we put this hour here, here, or here. When they meet, the coordinates of the position on the x-axis will be the same. So, x1 equals to x. We put here right sides of equations of motion and calculate time the cars met. Cars will meet at 10 o'clock. Not 10 hours later. First car begin to move at 2 o'clock, so he has been moving for 10 minus 2, this is 8 hours. Second car departed at 3 o'clock, so he has been moving for 10 minus 3, this is 7 hours. Now we can calculate coordinate of position of the place they met. It is enough to put 10 hour to one of equations of motion. It is done here and here. We see that the vehicles will meet at the coordinate minus 40 kilometers on the x-axis. Now we can solve this task graphically. In this table, we will calculate coordinates of position for both cars. We can put time to equations of motion here and here. But we know that first car at 2 o'clock was in the city A, so its coordinate of position equaled to minus 200 kilometers. And second car at 3 o'clock was in city B, so its coordinate of position equaled to minus 600 kilometers. Every hour, the coordinate of position of first car increased by 20 kilometers and second car by 80 kilometers. So we can add 20 here and 80 here. Now we can represent the motion of cars in xt coordinate system. We read the time and coordinate of the intersection of the lines representing the movement of both cars. It will be time and coordinate of the place where the cars met. So, we solved our problem. So, it is the end of this lesson.